Wonderful. Okay, good afternoon, everybody. Next slide, please. What I'd like us to do here is to work through a case study, but the backdrop of it, the context, is the increasing pressure that we see for the waste to energy sector, and it's been touched upon over the last few days. The increasing regulatory burden, the need for ever lowered emission limits, and also it can be a contentious contentious industrial sector in terms of the general population. So the process operators have a lot of responsibilities to face up to. And what I'm going to do is use a case study to help demonstrate how, with certain process controls, we can actually achieve benefits for both the process operator and also for the wider community. Next slide, please. I mean, the challenges that we see, of course, are, those lower emission limits that I've mentioned, the need to comply with all this associated regulatory standards. And using waste to energy sector as an example here, 2 years ago, there was the introduction of the recent BREFNO 2019, and that's guiding the sector in terms of best practice and how to generally operate and achieve the lower emission limits that we see. To give context to the pressures that we see for certain sectors and specifically with new applications, to give an example from the UK, from where I'm based, we actually see groups such as the UK Without Incineration Network, who are very much opposed to the idea of additional incinerators on the perception that they give a significant health impact through the pollutant releases. My personal take is it's actually one of, if not the most tightly regulated sectors, certainly within Europe, and actually a well-maintained incineration plant is generally relatively clean, and there are far worse industrial processes out there. So the point there is that, these process operators have to be able to demonstrate a strong environmental policy and ethical stewardship to the community. Next slide, please. Alongside those challenges, there are also other challenges that the process operators see, and not just within waste incineration, but across the wider industrial spectrum. Increased energy costs, increased material costs. And as at ENVEA, we face these challenges as many other manufacturing businesses do now. The supply chain is much harder. Lots of raw material costs have increased in recent months and years. And that includes materials used for the pollution control in the waste incineration sector, such as the sorbent costs, the sorbent materials that are used to help minimise some of the emissions, filter media costs. And, the routine challenges that the process operator faces, such as being able to ensure the efficient and smooth operation of the facility without any unwanted delays, such as blockages that adds just costs through direct labour costs, and also delays in production output or energy output in this case. Next slide, please. To give a very basic overview of a waste incinerator, we have the waste coming in, the combustion process itself. This then drives the turbines to generate the electricity. And from the waste gases that are generated, there are numerous abatement techniques they use. And these comprise various dry scrubbers, wet scrubbers, and ultimately the final emission, what is typically a fabric filter, a baghouse, which is used to get the emission limits right down to the very, very low levels that we see that are required under the European BREFNOs and BATC documents. Next slide, please. So when we look at the CEMS that are required, it'd be wonderful to go into detail about the complete range of emissions monitoring products that are required to demonstrate their legal compliance. Dust monitors, flow monitors, gas monitors, biogenic CO2 monitoring systems, now mercury, dioxins, and ultimately the need for appropriate software and data acquisition systems to be able to do the required reporting. That's just a simple overview to see what's required on their routine environmental compliance side with regard to their stack emissions. Next slide, please. But what I want to do here in this is not to focus on the emissions monitors themselves, but actually how we can introduce certain process monitoring tools to help achieve a better environmental outcome in terms of potentially the emission limits, the emission levels themselves, and also raw material costs. Next slide, please. This is a very simple and overview of just some of the products that we consider here. We can consider in terms of process monitoring to achieve certain efficiencies. We would not have the time in this short 15-minute session to be able to go into each of them in detail, but we can go from baghouse filter monitoring, level detection to ensure no blockages, flow detection, raw gas monitoring to ensure combustion control, and in-process gas monitoring as well. But for this study, for the purposes of the case study, we can't look into all of those. So what I'd like to do, next slide please, is to be able to focus on just two aspects here, and using mercury monitoring, as obviously is one of the most toxic materials, one of the most toxic pollutants that we see from waste incineration. One of the key challenges that the process operator has here is the inherent variability of the feedstock, and very little direct, or certainly limited direct control that we can have in terms of that as a feed material, as a fuel source. So what we're looking at doing here in terms of trying to achieve some process monitoring and environmental beneficial outcomes is to have monitoring of both mercury within the raw gas, straight from the direct combustion, and also to be able to monitor and control the reagents that are used, specifically hydrated lime and activated carbon. Next slide, please. So what we've got here is a number of different scenarios. So this was a series of tests that were undertaken through my colleagues in France on some of their on one of their waste incineration customers. So in the first example, let's call it case one. This is just doing it in the basic way. The norm here is to have a constant stream of dosing applied to the emission stream, with no upstream monitoring whatsoever. The second example, we are introducing some reagent control. Sorry, to go back, in the first case, we're just relying upon the mercury monitoring from the releases and with no reagent control, just a fixed rate. So for the second example, we are actually introducing some reagent control in the dosing, but still only relying upon downstream monitoring of the mercury emissions. And then in the third example, we're actually introducing some raw gas monitoring for the ammonia, and also upstream and downstream monitoring of the reagent control. So we have a variety of different scenarios here. Next slide, please. So this is a quick overview of the basic data that's used in this calculation, standard operating terms, detail on how many emission peaks they typically expect to see a day, and the duration of those peaks. It's worth noting here that unlike some of the gases that we're monitoring, the latency period or lag period, shall we say, for mercury, it's not a short spike that we see in the emissions. It's actually, it's a tailing curve, and these can last a number of hours, several hours. And here we've got some indicative costs on the sorbents. Unfortunately, my colleagues were not able to get costs for each and every sorbent, but it gives us a start point to be able to look at the outcomes from the different scenarios that we'll see. Next slide, please. So here, and this is the first set of data that we obtained. So if we refer back to the cases that are mentioned, so in the first one, this is just a constant flow rate of the reagents with no downstream monitoring. And what we see here is an estimated annual cost of about 34,000 euros a year. It's actually potentially going to be higher that these days, but this gives us a baseline for this case study example. So in the second example, when we start to control the reagent regulation, sorry, the reagent introduction, based on the raw gas monitoring and trying to optimize it. In when we see a peak, we can add more. When we don't see a peak, we can use less. So actually there, the duration of the peaks are typically lasting up to about 3 hours. But actually by not applying the fixed rate and starting with a lower base rate, so where we've decreased the background sorbent level by about a factor of 3, from 1 kilo per ton incinerated down to 0.3 kilos per ton incinerated. That alone, and upping the dosing only for when we detect the peaks and the outputs, that's decreased the sorbent cost to about 22,000 euros a year. So a significant cost has already been achieved there. And then the third example, where we've actually got the raw gas monitoring to give us real-time data on what's directly coming out of the combustion process for the mercury itself, with the reagent control, by working on this, again, keeping that lower level of standard dosing, but increasing the dosing when we see the peaks. That's brought two benefits here. It's actually decreasing the peaks, instead of them lasting 3 hours, they're now down to 2 hours. And also in turn decreasing the sorbent cost further down to 18,000 euros per year. So that gives us cost savings of between 11 to 15,000 euros a year by this approach in this example. Next slide, please. In case study B, the key difference that we see, although there was a slight difference in the sorbent mix, but the aim here was to decrease the baseline sorbent level down to 0.16 kilos per ton, kilos of sorbent material per ton of waste incinerated. Everything else is essentially the same. Next slide, please. So here, the cost of the sorbent, as I said, it's a different sorbent mix, but the baseline start point, with no upstream monitoring, no reagent dosing, in this example was 81,000 euros per year for this study. But then when we move to case study 2, where we're introducing the reagent control, where we're using the CEMS data, the emissions data to increase the dosing, the peaks themselves are still lasting typically 3 hours, but actually we've almost halved the reagent costs in this approach by getting it down to 47,000 euros per year. And then for the third and final example of the case study, the kind of the optimum, shall we say, where we have upstream the raw gas mercury monitoring, and also the upstream and downstream reagent control for the mercury monitoring. Again, the peaks of the mercury duration, the decreasing down to 2 hours typically. And the annual cost of the sorbent is decreased once again, so down to £36,000 a year, 36,000 euros per year. So again, we're seeing a significant decrease in the sorbent cost, with the added benefit of actually decreasing the mercury emissions as well, and certainly through the duration of the peak. So here, in this case study, the cost savings are between 34 and 45,000 euros per year. So, roughly halving it in round numbers. Next slide, please. So just to conclude this, there was a lot to try and capture in 15 minutes. It's a short time slot. So, for the waste incineration sector, the general guidance that's provided to achieve environmental compliance and process efficiency is through the BREF and the BATC documents, the last one being introduced in 2019, as mentioned earlier. But in addition to this, what we can do is we can focus upstream into the process and bring in further monitoring techniques, such as the raw gas monitoring, the dosing control. And as we saw through these two case studies, the outcome of this is several, really. So several outcomes. We've got reduced sorbent costs, we've got better control of the emission peaks and keeping those down. That's further adding to the legislative compliance. And these are both giving, real-time cost savings for the process operator, but also it adds us to the ethical stewardship. This is a very positive message that the operator can give back to the local community, especially where we do see, this can be quite contentious in some areas. So I thank you for your time. Last and final slide. There was a lot for me to get through there in 15 minutes, but hopefully you got an insight as to how looking upstream with process monitoring can give some real positive environmental and social benefits back to the waste incinerator and his process. Thank you very much.